Okay, so we continue. Okay, so we have another type of work. Okay, so this is work of spring. Okay, so I'm sorry, I just erased, okay, from the last video in part 1. It is work of weight. Here it is work of spring. Okay, so work of weight is actually a negative work. So here, work of spring, just like the work of weight, is also a negative work, unlike those all these previous three. It's positive work. Here is it's also a negative work. So in a spring, it has a spring constant, which is K. Okay, so this spring constant um, represents uh, a property of the spring, okay, which is unique to each type of spring. So in which if you applied a certain force, for example in kilonewton or libra, okay, so it means that as you pull the spring into a certain degree, the force applied will increase relative uh, to the displacement. So this is what we call the spring constant. So 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 due to this, okay, so you can use your spring. Okay, you can compute um, the work done by the spring. Okay, let us say U from 1 to 2, spring is equivalent to 1/2. Okay, so let us say you have this initial position of S1 and then a final position of S2. So um, your work will be negative. Okay, so negative 1/2 K multiplied, okay, quantity S2 squared, or S of 2 squared times minus S of 1 squared. Or, okay, okay, so that is how you compute the work done by the spring. Okay, so we'll continue now. Okay, in another topic. Okay, so we have done with work. Okay, so let us discuss about energy. This portion about energy. Okay, so it has the same unit with work. It could be in kilonewton meter or libra foot, but somehow okay, so first of all I will erase. So we'll have here energy. Okay, okay, so energy, it can be in the form of kinetic energy, and we have potential energy. So kinetic energy is energy in motion. Okay, okay, so kinetic energy is energy in motion, while potential energy is energy at test. Okay. So this is the basic definitions you might have encountered during your high school days. Kinetic energy and potential energy. Okay. So in some books, just kinetic energy can be denoted as either KE, okay, or T. Okay. Sometimes it is denoted as KE simply because it's kinetic energy, and then or T. Okay. So potential energy can be denoted as PE or V. Okay. So um, so uh, so by the law, okay, so by law of conservation, okay, by law of conservation of energy, we can denote that KE, okay, plus PE, okay, at a certain position is equivalent to the final KE and PE. Okay, so so it means that at a certain position, okay, so let us say you have a particle here standing at a certain elevation. Let us say it is at the top of a hill, and it is located, okay, at a distance d, let us say no y, let us say y at the top. Okay, so at this point, let us say this is okay, this is at initial position. Let us say this is 1, okay, its position, okay, and then let us say that if this particle will roll down at this portion, okay, at any moment, let us say it rolls downhill. Let us say this is y sub 1 and this is y2. Okay, so let us say this is the initial condition at initial okay, at 1, okay, and then this is 2. Okay, so at a portion when it is at the top of the hill, this is denoted as the initial, okay, the one let us say at okay, at point 1, let us say it is here at point 1 and here it is point 2. Okay, at the time in which it rolls down. So according to the law of conservation of energy, if you add your kinetic energy and potential energy at any moment, okay, it will be equivalent to its final sum of kinetic and potential energy respectively, meaning at any time, energy at the beginning will be energy, okay, energy 1 will be equal to energy 2 at any time. So in which your energy at the at 1 is equivalent to KE1 plus PE1, or and at that 2 it would be kinetic energy 2 plus potential energy at point 2. Okay, it could also be denoted as, okay, since KE1 can also be denoted as T, so it could be rewritten also as T1 or T sub 1 plus, okay, it's conserved. Okay, so we can denote this as T. I will just put it here. T sub 1 plus V sub 1 is equal to T sub 2 plus V sub 2. Okay, so this is if all, okay, so this is if conservative, let us say all forces are conservative. Okay, so when we say conservative, it talks about all types of energy that is not dependent on the path. Okay, so we are just talking about its initial position. Okay, so let us say your initial position is at 1, or initial point or initial position, and then your final position. So if that is the case, we are talking about its position relative to y-axis, or any axis, x-axis or y-axis. Okay, so it's not dependent on the path. Okay, so let us, okay, so that is all forces are conservative. Okay, so I just want to put it here. Okay, the definition of conservative forces. Okay, so you don't work, so we will have more examples, okay, as we discuss, so that we will understand what is these conservative forces. And okay, so conservative force is so independent, so it is independent on the path taken. So it doesn't matter, it doesn't okay, so the path here is here, this. Okay, so this type of forces, okay, so when we say conservative forces, all the types of forces relies only on the position, on the initial and final position of the particle relative to y-axis. Okay, so these forces, okay, forces that are independent of the path taken. Okay, so the amount of okay, so and then we have these non-conservative forces. So when non-conservative forces includes, okay, so we includes the work, okay, work done by the non-conservative forces. So if there is a non-conservative forces, this is not only KE sub 1 plus PE sub 1. We includes work from 1 to 2. Okay. So maybe okay. So non-conservative forces are forces that are dependent on the path taken. So one good example is of this is what we call friction. Okay, so the most basic type of non-conservative forces, or the most common, is the friction. Okay, so here we'll concentrate on this one, the law of conservation of energy, in which all forces are conservative, in which the initial energy is equal to the final energy. So this is the formula. Okay, so in the book, especially in Hibbeler and other books, they use this, in which this is your kinetic energy and your V is the potential energy. Okay, so don't be confused. Okay, it depends upon what book you are reading with. So your book might be using Ke for kinetic energy. It can be also denoted as T in other books. Other books use Pe for potential energy. Other books use V for their potential energy. Okay, so these equations, this equation is applicable when all the forces involved are conservative. Okay, but if a friction or work, is involved, there will be a different there will be another so there will be another equation in which we can say that your so let us write it in both ways. Whether you use your Ke or Pe, so we have so let us say involves non-conservative forces also. So if that is the case, you can write an equation like Ke at 1 plus Pe 1 plus, so when we say non-conservative forces, there is a work involved. Work of non-conservative forces relative to the path taken. So 1 to 2 is equivalent to Ke sub 2 plus Pe sub 2. So this is work. So some books use Ke for kinetic energy, Pe for potential energy, and W for work. But somehow, in some books, it is written as this. T sub 1, for Ke. Instead of Ke, we use T. And then for potential energy, instead of Pe, we use V1. And instead of W for work, we use U, or U sub 1. U1 to 2, is equivalent to T sub 2 plus V sub 2. So this, so please take note, I will just put NC here, NC. Non-conservative forces. But somehow, I would like to reiterate, that change. So this is, U1 to 2, NC is a work of non-conservative forces. But also, I would like to explain, that if there is a work of non-conservative forces, this is also, there is also a work of, um, there is also a work of conservative forces. Okay. So if there is a U1 to 2 NC or work of non-conservative forces, there is also work of conservative forces. And that, okay, so maybe I will put, okay, so you can, since this is a video, you can replay the portion in which is not clear to you. Okay, so maybe I should erase these definitions to have some space. Okay, so just like just what I said. Okay, okay. So if it involves non-conservative forces, you use this formula. Okay, so these are equivalent depending on what reference you are using. But somehow, let's go back. Okay, so when all the things, okay, so when all kinetic when all of the forces involved are conservative, so here we can rewrite actually, okay, so the work, or let us say W, okay, let us say we use the work from 1 to 2 conservative is equivalent to the change in potential energy. Okay, so that is 1, which means, okay, actually it's actually the negative, okay, sorry, the negative change in potential energy. Okay, so the negative change in potential energy is equivalent to the work of non-conservative forces. Okay, so therefore, okay, so from this problem we have KE1 plus PE1 is equal to KE2 plus PE2, and we know that the change in PE is equivalent to negative of PE2 minus PE1. Okay, so therefore, okay, I will just write it, so it will be equivalent to KE1 plus, okay, so please remember this formula. Okay, KE1, okay, this negative change in PE is equivalent to negative of quantity PE2 minus PE1. Okay, that's, so I would like to clarify this. Okay, so conserve space, it's equivalent to the negative change in PE, or this is equivalent to negative of PE2 minus PE1. Okay, so since, or also equivalent to PE1 minus PE2. Okay, so since we multiply the negative, so we transfer it here, the PE2 to the left. So therefore we can get this formula, which KE1, since this is equivalent to work of conservative forces, so we use W1-2C is equivalent to the work kinetic energy 2. Okay, so in other words, okay, so we okay, so we use these denotations T, U, and V. Okay, So you can actually rewrite this as, okay, you can also rewrite this since, so in other books, instead of W, you use U. So U1 to 2C is equal to negative, okay, negative change in V. Okay, so where V here, okay, is the potential energy. So you can use, instead of this formula, you use this formula depending on the denotation of the reference you are using. And then we have, okay, you can convert this one into in this form in which T1 is kinetic energy and V is the potential energy. So we have, and U is the work. So we have T1 plus, okay, the work involved of conservative energy, which is U1 2C is equivalent to T2, okay, where your 1 is the initial position and your 2 is the final position. Okay, so you can use any of these two. Okay, so they just have different denotations, but this formula and this formula are the same, and this formula and this formula are technically the same. Okay, so I use two different denotations, okay, depending on what reference you are using. Okay, so I hope you understand. Okay, so since this is video, you are free to replay the portions of the lecture in which isn't clear to you yet. Okay, so we will continue on the next video. We will continue the lecture in another video. Okay,